Welcome back to the Deep Dive. Today, we are looking under the hood of, well, the engine that's driving the modern world. We are talking about the architecture of AI.
We are.
And frankly, the engine we're all using right now, the Transformer, it's getting a little inefficient. Starting to feel like driving a tank to the grocery store.
It is powerful. There's no doubt about that. But, inefficient is putting it politely. It's a total gas guzzler.
Right.
And as we demand longer and longer context windows, uploading whole books or huge code bases, that tank is just running out of fuel.
Exactly. And we've got a stack of research today that suggests the dominance of the Transformer. The tech behind ChatGPT, Claude, all of them might be facing a really serious challenge.
A real challenger.
We're looking at a resurgence of an older idea, the linear RNN, the recurrent neural network.
Which is such a fascinating twist, isn't it? Because RNNs were the old guard. They were the standard before Transformers just, wiped the floor with them back in 2017.
Right.
But the papers we're covering today on architectures like Kamba, RLA, ENA, and the RWKV7 updates, they suggest they're making a very serious, very high-tech comeback. These are not the RNNs you remember from 10 years ago.
So here is our mission for today. We need to figure out if these new, faster linear models have actually solved their biggest problem.
Which was?
Stupidity. Can they finally match the intelligence of the heavyweights without eating up all the memory in the world?
That is the core tension right there. It's a battle between perfect memory and efficiency, and you usually can't have both.
Okay, so let's set the stage for you before we dive into the papers. Why is the Transformer so heavy, and why is the RNN considered so fast?
It all comes down to how they handle history. So imagine you're reading a mystery novel,
Right.
a Transformer, to predict the next word on page 300. It essentially rereads every single previous word on every page up to that point. It compares everything to everything. That's what we call quadratic complexity.
Meaning if you double the length of the book, the work doesn't just double.
No, it quadruples. It just explodes. And that's why running a million-token context window costs an absolute fortune. It's perfect memory, sure, but it's mathematically just so expensive.
Whereas the linear RNN,
The linear RNN is more like a human reader. It reads a sentence, it compresses the meaning into a kind of mental gist, what we call a state, and then it moves on.
doesn't look back.
It doesn't look back at the raw words on page 1. It just relies on its memory of them. This is linear complexity. It's super fast. But the trade-off has always been that the compression is lossy.
Meaning when it compresses that chapter into a gist, it forgets the specific details.
Exactly. It has a senior moment. It forgets the phone number you mentioned 3 pages ago because, well, it didn't think it was important at the time. It gets overwhelmed.
So the goal of this entire stack of research, Kamba, RLA, ENA,
Yeah.
is basically how do we stop the RNN from forgetting the important stuff without losing that linear speed?
Precisely. We want the speed of the RNN with the recall of the Transformer. And the roadmap for today, it involves 3 frontiers. First, architecture. We're looking at Kamba and RLA for how we structure this memory better.
Okay.
Second is modality. How do we get these text-based brains to actually see images and video? And third, adaptability, which is the wildest part. Can we actually change the model's brain structure while it's taking a test?
Let's start with architecture then.
Yeah.
We have this paper on Kamba. It's trying to fix a very specific flaw in the current fast models, like Mamba or GLA. What is that flaw?
The authors of the Kamba paper, they point out something really critical. They describe standard linear RNNs as having linear key-value memory registers.
Okay, that is a mouthful of jargon. Can you translate that?
Right. Think of a filing cabinet. In a standard linear model, you are just shoving files in one by one. But you don't have a smart system for deciding which old files to shred to make room for new ones.
Right.
You just have a simple decay rule. It's like saying every file gets 10% less important every hour.
So I'm forgetting my wedding anniversary at the exact same rate that I'm forgetting what I had for breakfast.
Exactly. It's uniform forgetting. It just lacks a criterion for what to keep. And this is why they fail at specific recall. Kamba fixes this by introducing the concept of a bilinear system.
Bilinear.
Yeah. In the old linear models, the input just gets added to the pile. In a bilinear system, the internal state actually interacts with the input.
So the current memory kind of talks to the new information before it accepts it.
Yes. But Kamba goes a step further. They use closed-loop control.
Now that sounds like engineering theory.
It is, and it's brilliant. Think of a simple heater versus a thermostat. A dumb heater just blasts heat, right? Regardless of the room temperature.
Sure.
A thermostat, that's a closed-loop system. It measures the temperature and adjusts its output based on that feedback. Comba applies feedback control to the query vector during output.
Okay, so before it speaks or predicts the next token, it checks its own memory state to refine what it's looking for.
In a way, yes. It uses this scalar plus low rank update rule. The math isn't important. Just imagine it has a very specific, efficient formula to update its memory. But the key is that feedback. It filters the noise. It decides, okay, this input is filler, throw it away. This input is a crucial date, lock it in.
But wouldn't that slow it down?
Right.
Adding a feedback loop sounds computationally expensive.
You'd think so, but the implementation is key here. They wrote it in Triton, which is a language specifically for writing high-performance GPU code.
Ah,
And because the math is still fundamentally linear, it's just lightning fast. It's beating previous models like Mamba in both language and vision tasks simply because it's smarter about memory management.
so Comba builds a better filing cabinet. It organizes the files better. But even the best filing system makes mistakes.
Of course.
You file something wrong or you misremember a fact. Which brings us to our next paper, RLA, or Enhancing Linear Attention with Residual Learning.
Right, this is the oops factor.
Exactly. The paper talks about a bottleneck in how these models correct themselves. What is that bottleneck?
So, in standard linear attention, if the model realizes, wait a minute, I predicted the wrong thing 5 words ago, it has to use the current incoming word to correct its entire memory state.
So it has to fix the past using only the present moment.
Yes, it relies on one single piece of new information to fix a systematic error in its brain. I mean, that is a massive bottleneck. It limits how expressive the model can be because it's constantly playing catch-up with these limited tools. It's like trying to steer a cruise ship by, paddling with your hands.
So how does RLA fix that?
They introduce an auxiliary state,
A second brain.
more like a shadow memory, a parallel track. This auxiliary state, it explicitly tracks the residual, the difference between what the model predicted and what actually happened.
Ah, so if it predicted the cat sat on the mat, but the text actually said the cat sat on the hat, this shadow track records that error.
Exactly. And it accumulates those errors over time. It's very similar to gradient boosting in traditional machine learning, where you train a second model just to fix the mistakes of the first one. But here, it's all integrated into the architecture itself.
But doesn't running a parallel memory track double the computational cost? I thought we were supposed to be efficient here.
That's the clever part.
If we keep adding tracks, aren't we just rebuilding a transformer?
No, it adds very little overhead because it's still linear. It's just another fast stream of numbers. They use a dedicated correction factor called gamma to control how much this oops track influences the final answer. And crucially, they use something called residual clipping.
Clipping.
Yeah. Imagine if you kept focusing on your mistakes too much. You'd get paralyzed, right? Or you'd overcorrect.
Sure.
Residual clipping makes sure the error corrections don't get too loud and destabilize the whole system. It just keeps the oops detector in check.
And the results? Does this actually help it remember things?
Oh, it's stark. It beats Mamba 2 and RetNet on needle-in-a-haystack retrieval tasks.
And that's the gold standard test, right?
Yeah.
Can you find this one specific password buried in a 500-page book?
It is. And that's traditionally where RNNs fail miserably because they've already compressed that password into a blur.
Right.
RLA proves that if you track your errors separately, you can keep that needle sharp. You don't blur the mistake into the background.
Okay, so we've got feedback loops with Comba, error correction with RLA. But we've been talking mostly about text, words in a line.
Right.
The real world is visual.
And that is the hardest pivot for these models to make.
This is the modality frontier. We have the ENA paper, Efficient N-Dimensional Attention. Why do linear RNNs struggle so much with a simple JPEG?
Because RNNs love lines. They are 1D processors. Time flows forward 1 second at a time. But an image is 2D. A pixel's neighbor isn't just the one before and after it. It's the one above it, below it, diagonal to it.
So how do they used to handle this?
The old method was called scanning. You basically take the image and slice it up into a long snake. You flatten the 2D grid into a 1D line.
I've seen those diagrams. It looks clumsy.
It's brutal. The source material is actually pretty savage about it. They say scanning provides limited benefits. I mean, think about it. If you flatten an image, a pixel, and its neighbor directly below it might end up thousands of steps apart in that line.
You destroy the local context.
Completely. The model just loses track of shapes. You lose the spatial relationship.
So what does ENA do?
It proposes a hybrid approach. It says, okay, let's use the linear RNN part to capture the global context. Is this a picture of a beach or a forest? But let's use something else for the detail.
And that something else is?
Sliding tile attention.
Is that different from sliding window?
What?
I know in sliding window, you're just looking at the few pixels around you.
It's a crucial hardware distinction. A sliding window usually moves pixel by pixel. For a GPU, which loves to process big blocks of data all at once, pixel by pixel is slow. It creates these mixed blocks of memory that are hard to parallelize.
So it clogs up the pipes.
Exactly. Sliding tile moves in chunks. It grabs a 4x4 or an 8x8 tile of the image and processes the attention within that tile. It aligns perfectly with how GPUs want to work.
So it's hardware-friendly, local attention.
Yes. And here is the killer insight from the paper, the main takeaway. ENA shows you do not need full attention, where every pixel looks at every other pixel. They found that about 70% sparsity works just as well.
70%. You can ignore 70% of the connections.
And still match transformer performance on ImageNet and video generation. It turns out, for vision, you mostly need to know what your immediate neighbors are doing, plus have a general idea of the whole image. You don't need the top left corner pixel to have a deep conversation with the bottom right corner pixel.
That actually makes intuitive sense. So ENA is basically admitting we aren't just trying to make RNNs act like transformers anymore. We're mixing the global compression of the RNN with the local focus of attention.
It's the best of both worlds, and it's much, much faster to generate video this way.
All right, let's pivot to adaptability. This next paper on RWKV7, it kind of blew my mind a little bit. It's about state tuning.
Oh, this is the one. This is the Matrix download moment. I know Kung Fu.
Exactly. The premise here is wild. Usually when we test a model, its brain is frozen, the training is done, the weights are locked.
Right.
But this paper asks, what if you could make a model smarter during the test without actually retraining its weights?
And to explain why that's so revolutionary, we have to distinguish between weights and state. The weights are the long-term memory, the synapses of the brain. That costs millions of dollars to train.
Right.
The state is the short-term memory. It's what is in your mind right now.
Okay, so weights are the hard drive, state is the RAM.
That's a good enough analogy. In a normal RNN, the state is determined strictly by the input. You read a sentence, your state updates. It's a passive process. This RWKV7 paper says, no, let's treat the state matrix as a variable to be optimized.
So we aren't changing the brain structure, we're changing the brain waves.
That's a fantastic way to put it. They focus on the RWKV7 model, specifically the Goose version, and they use a technique called state tuning. They run an optimization loop at test time to adjust the state matrix for that specific problem.
How can they do that efficiently?
Two main ways. First, a kernel method. They dynamically upscale the state size. They project the memory into a higher dimension to capture complex patterns, and then project it back down.
Yeah, and the second way?
They use DBP, decorrelated backpropagation.
Okay, break that one down. That sounds heavy.
Well, when a model learns, often its neurons all start firing together in a pump. They get correlated, it's inefficient.
Right.
DBP forces the features in the state to be independent decorrelated. It spreads the information out. This speeds up the learning process drastically because each neuron is now doing something unique.
But the part that really stood out to me was the teacher aspect.
Yes. Test time scaling with larger model guidance. This is where it gets so practical. They take a massive 70 billion parameter model, a supercomputer brain, and have it generate a chain of thought for a difficult math problem.
So the big brain shows its work.
It shows its work, right. Then they take the tiny RWKV7 model and they tune its state to match that reasoning path. They aren't training the tiny model to be smarter overall. They're tuning its current mental state to mimic the smart model for just this one problem.
It's like a student downloading the teacher's focus for 5 minutes just to pass an exam.
And the result is the small model creates a state that allows it to outperform significantly larger models on math tasks like GSM-8K and science tasks like ARCC. It's punching way, way above its weight class because its state is optimized.
That is just wild. It suggests that a lot of what we call intelligence in these models isn't necessarily about having a trillion parameters. It's about having the right context loaded into the working memory.
It effectively challenges that whole bigger is better dogma. Maybe we don't need bigger brains. Maybe we just need better focus.
Okay, so we have all these new architectures, Kamba, RLA, ENA, RWKB7. They all claim to be the best. But, you know, as a skeptic, I have to ask, how do we actually know?
That's the million-dollar question.
Benchmarks are notoriously easy to game. Every single paper claims state-of-the-art.
And that leads us to the final piece of our stack today, selective bench.
The benchmark paper.
Exactly. Standard benchmarks test general knowledge. Who was the first president? Selective bench is different. It's a surgical tool designed to test one specific cognitive skill: selectivity.
Selectivity meaning knowing what to keep and what to throw away.
Precisely. Can you filter noise? They break it down to these fascinating tasks. One is noise rejection. They insert random garbage sequences between the important data, like static on a radio. Can the model ignore it?
Most models should be able to do that, right? That seems basic.
You'd be surprised. If the model is just blindly absorbing the next token, that garbage corrupts its memory. But the harder task is context-aware selectivity. This is where they insert distractors that look like data but break the rules, non-grammatical gaps, or false info that contradicts the context.
So it's like someone whispering wrong answers in your ear while you're trying to listen to a lecture.
That's it, exactly. And the results from this give us a blueprint for what features actually matter in these architectures.
So what's the verdict? Who wins?
Well, it depends on what you want. The benchmark found that for pure recall, just remembering things, you need gating and you need fast forgetting.
Fast forgetting, as it tends completely counterintuitive.
Think about it, though. If you can't dump the garbage immediately, your memory fills up with junk.
Oh, okay.
The benchmark showed that models like Mamba 2 and gated DeltaNet do really well here because they have strong gates mechanisms to slam the door on useless info. The standard DeltaNet struggled because it couldn't clear its memory fast enough. It had weak selectivity.
Interesting. So to remember, well, you have to be good at forgetting. What about for generalization? For reasoning about new things?
For that, you need channel mixing. This is where the model mixes information between different memory channels inside its state. Models like gated delta products shown here. If you want to understand patterns that extend beyond what you saw in training, you need that internal crosstalk.
And where does our old friend, the expensive transformer, sit in all this?
The transformer, with its softmax attention, is still the undisputed king of raw memory capacity. Because it doesn't compress history, it doesn't lose anything. But, and this is the big but revealed by selective bench, it fails hard at extrapolation.
Length generalization.
Yes. If you train a transformer on sequences of length 1,000 and then test it on length 2,000, it often just falls apart. It doesn't know how to handle the positions. The linear RNNs, especially the ones with channel mixing, were much better at handling lengths they hadn't seen before.
Right.
Because they're learning the pattern of the sequence, not just memorizing the position of the words.
So if you want perfect recall of a short legal document, maybe use a transformer. But if you want to reason over a book you've never read before or a sequence that goes on forever, maybe look at these new RNNs.
That's a pretty fair synthesis. The transformer is a library. The RNN is a researcher.
Okay, let's unpack this whole stack. We started with the idea that transformers are dominant but inefficient. We looked at Kamba adding feedback loops,
RLA adding error correction tracks,
ENA mixing in local attention tiles, and RWKV7 tuning the state on the fly.
The big picture here is convergence. We aren't really seeing pure RNNs anymore. We are seeing these complex hybrid systems. We're taking the speed of the RNN, that linear complexity, and we're just bolting on the smarts of the transformer.
We're adding the feedback loops, the error correction.
And we're learning that state is a malleable thing. The RWKV7 paper really drives that home. The distinction between training and inference is getting blurry. If I can tune the state at test time, the model is essentially learning while it's working.
It feels like we're moving from static libraries where you just look up info to active reasoning agents that can adjust their focus on the fly.
And critically, we are doing it efficiently. All of these papers emphasize linear speed. They want to run on your laptop, not just in a massive server farm. This brings high-level AI to the edge.
Which is exciting for those of us who don't have a spare data center in the garage.
Definitely. It democratizes the technology.
So here's a thought to leave you with. If we can tune a model's state on the fly to match a supercomputer's reasoning, like we saw with RWKV7, do we eventually reach a point where we just stop making the models bigger?
That is the question, isn't it? We've been in this scaling law era where size was everything.
Right, but instead of training a 100 trillion parameter model, do we just build a really good medium-sized model and then spend all our energy optimizing its state and context for the specific problem at hand?
It's the difference between having a bigger brain and just focusing harder. And if these papers are any indication, focus might be the next frontier of AI scaling.
Focus is the new scale. I like that. Thanks for guiding us through the stack today.
My pleasure. It was a lot of fun.
And thank you for listening. Until the next deep dive, keep learning.